Welcome, dear friends. We will do today our 12th video lecture on differential geometry. Last time we studied connection forms and structural equations. Now I'll do one example. Uh, Example will be on spherical coordinates. Okay, so consider the spherical coordinates given by uh, okay, as usual, x1 is rho times cosine uh, v cosine nu, x2 is similarly cosine nu, and x3 is rho times sine nu. Here okay, so uh, rho will be our first variable, phi will be our second variable, and nu will be our third variable. Okay, because I'll use sometimes uh, these indices. Okay, now we know that uh, theta I, the dual forms, are given in terms of the matrix Aij, the attitude matrix, where, remember, Aij was Ei dot product Uj. Ei is the ith coordinate of the adapted frame, and Ui's are the standard natural frames on R3. What about Ei's? So this adapted frame. Well, to find E1, E2, E3, what we will do, so we will just take the ith, sorry, derivative of x1, x2, x3. So I'll just take del x rho, my first coordinate of x1, x2, x3. So this will give me a vector, and then I'll just divide it by its length. Okay, so let me write. Okay, x1, x2, x3. So if you do this, let's see what we get. So derivative of this with respect to rho is just cosine phi cosine nu sine phi cosine nu and sine nu, and then norm of this. What is the norm of this? Square of this one plus square of this one. That will give me cosine squared nu, and then square of this one, which is sine squared of nu. So in total they will give me just 1. Therefore E1 is just this vector. Okay, all right, now what is A11 and so AIJs are just the dot product of AI with UJ. So sorry, uh, if I take dot product of this with U1, I'll get the first coordinate. So this is A11. So let me write also those. So this is A11. This is A12, and this is A13. Similarly, by just taking derivatives with respect to this time the second derivative, second variable, which is phi. Uh, so I'll just take derivative of this with respect to that and divide by the norm. Divide by the norm. Let me tell you what you will get. When you take the derivative, you get minus rho sine cosine nu rho cosine phi cosine nu, and then third coordinate is independent of the second variable, and then divide by the norm of this. What is the norm of this? Square of this plus square of this. So sine squared cosine squared will give me v, and then add them up and I'll get this. Okay, so when you divide with this, we get e2, which is uh, uh, okay, minus sine phi cosine phi and then 0. All right, so this is a21, a22, and a23, because aij is just ei dot uj. uh, ui's are the standard natural frames on R3, and similarly the third vector will be what? So I just take derivative with respect to the third coordinate nu. So this will give me minus sine v, minus sine v, and then this will give you cosine v. So let me write that down. Minus rho cosine phi sine nu minus rho sine phi sine nu, and then rho cosine nu, and then I have norm of this. Norm of this is just rho, so we get e3 minus cosine sine nu minus sine phi sine nu and cosine nu. So this is a31, this is a32, and this is a33. So we have computed the matrix, attitude matrix aij. Okay, what else? So and theta 1, which is a1j dxj, will be what? So this is just a11 dx1, a12 dx2, and a13 dx3. All right, so this will give me what? I know what ai's are, and what about x dx 1 dx2? Here the this is x1, so I'll just take differential of this, and differential of this. Let me do one of them. So a11 is just okay. A11 is this cosine phi cosine, sorry, nu, and then dx1, so here's x1. I'll take exterior derivative of that. Let me write it down here. This is cosine phi cosine nu d rho minus rho sine phi cosine nu d phi minus okay, so minus rho sine phi cosine nu d no, this is not correct, sorry, cosine phi sine nu d nu. Okay, so this is the first term yet, and then for the second term I have sine phi cosine nu times sine phi cosine nu d rho minus rho cosine phi cosine nu d phi minus rho sine phi sine nu d nu plus A13 is just sine nu times sine nu d rho plus rho times cosine nu d nu. All right, so this is a huge expression, but there will be a lot of cancellations, and the result is just d rho. Okay, so only this d rho term will survive, all the other ones will cancel each other. Well, one can calculate similarly uh, theta 1 sorry theta 2 is just rho times cosine phi d nu, and the third one is rho times d phi. Okay, all right, we know from Cartan's equations that uh, uh, we know that uh, connection 1 form is just the matrix A, its differential times its conjugate, or equivalently omega ij is just summation over k aj k dai k, and hence we computed all these, and hence we get omega 1 2 is just cosine omega 1 1 is just 0 because this is skew symmetric matrix, so I term is 0. 1 2 is just cosine phi d nu. 1 3 is just d phi, and 2 3 is sine phi d nu. The other terms are since this is skew symmetric, omega 2 1 is just minus cosine d nu, and similarly for the other ones. So we have computed now the matrix of omega ij's. Okay, we can go further now from the first structural equation. We can compute it. We can compute the derivatives of omega theta i's, and this was omega ij wedge product with theta j summation over j, and thus we may, for example, compute d theta 3. So this is omega 3 1 wedge theta 1 plus omega 3 2 wedge theta 2. And it turns out that, you know, if you just copy what we have done, see that we have this. And this is really which is the case since theta 3 was rho times the phi. Therefore, when you take x derivative of this, you really get this. Okay. What about the omega ij from the second structural equation? We get so similarly from the second structural equation, the omega ij is just omega ik which omega kj. Okay. Uh, and this is just okay. And say let's compute just one of them, omega 1 2. This is what, so I is 1, uh, j is 2, so this is summation omega 1 k wedge omega k 2. So what is this? Omega 1 1 is 0, omega 2 2 is 0. Therefore, we have only one non-zero term for k equals 3. So this is just omega 1 3 wedge omega 3 2. And we had computed omega ij's above. Right, so here, yes, omegas here. So by just plugging them, we get okay, so right, like this 1 3 wedge 3 2, and this is equal to minus sine phi d phi d nu. Okay, which is the case since you know d omega 1 2 is just d omega 1 2 was cosine phi d nu. So we verified you know, Cartan's equations formulas. All right, so this finishes section 2.8. Now we will start chapter 6, geometry of surfaces. In R3, and the first section is the fundamental equations, the fundamental equations. Okay, so what is this? We start with an adapted frame. So it's an adapted frame definition. An adapted frame field E1, E2, E3 on a region O in a surface in R3 is a Euclidean frame. So a set of three vector fields which form an orthonormal basis at each point, so that such that E3 is always normal to the surface. So E3 is the normal vector. Okay. So it's a frame so that let's say E1 is like this. Since E3 is normal, the other two should be tangent, of course. E2 is like this, and E3 is normal. Okay. All right. Okay. Of course, we have an adapted frame whenever our surface is orientable. If it is orientable, then we have always this E3 vector. And then how can we find E1, E2? For any surface chart, just write down two linearly independent tangent vectors, uh, and then apply, Gram-Schmidt process, find E1, E2, and then take their dot product, and you get the third vector E3. So there is an adapted frame field on a region or in M if and only if this is orientable. Let's see some examples. For example, for the cylinder, okay, we have this. Let's say this is E1, this is E2, and E3 will be this out normal vector. Okay, so this is an adapted frame. Similarly, for a sphere, okay, uh, let's say we have a point on a parallel here, like, and then we have also the, of course, uh, meridian, right? So let's say this is E1, this is E2, and again, so it will be like this, I guess. Yeah, E3. Maybe I should draw with different colors. Okay, so E1 is this vector, E2 is this vector, and E3 will be the cross product of this three, so E3 will be this. So E1, and this is E3, and this is E2. We know that each meridian intersects every parallel orthogonally. That's why E1 and E2 always a frame on the sphere, and E3 is just a cross product, so it is 0. Okay. Okay. we have another definition. We have defined connection one forms for a frame in R3. Now, for the adapted uh, frame on a surface, connection one forms uh, gets different names. So the uh, one forms omega ij defined by, we already defined these by the equation. Remember, what was the equation? Uh, so covariant derivative of ei along any vector is just omega ij v of ejp. So this is summation from 1 to 3 are called the connection one forms on the connection one forms on M. Okay. We have an immediate lemma. Uh, the shape operator on any vector is just omega 1 3 e1p plus omega 2 3 oops v e 2. Why is that? Proof is simple. We just write down the definition. Well, the shape operator is defined by minus the covariant derivative of E3, the normal vector in this case E3 along the vector V. And this is just from this uh, minus 3 1 minus 3 1 V E1P plus or minus 3 2 V E2P. So this is just equal to what? Since this is skew symmetric, one forms are skew symmetric, this is equal to this. So omega E2P. So the proof finishes. All right. As in the previous lecture, we define dual one forms given an adapted frame E1, E2, E3 for a region O in M. We define uh, the dual one forms theta 1, theta 2, theta 3 by the equation by theta I at V is just definition V dot V dot product EIP. So this was our definition for the dual one forms for a frame. Here, of course, since we are working on a surface, we take an adapted frame, meaning that the third vector is normal to the surface. Okay. Note that this vector, this form here is just what? Just v dot uh, e3p, and this is normal, therefore this is 0 for all vectors in the tangent plane. So this form is 0 on M, and hence theta 3 is identically 0, uh, identically 0 on the manifold, on the surface. Okay. Okay. Now here we have an again theorem, which is just the Cartan's you know uh, equations. If E1, E2, E3 is an adapted frame for M, then we have two statements. First, so the theta 1 is just 1 2 omega 1 2, which uh, this is just 2 1 theta 1. These are called first structural equations, is before uh, omega 3 1 wedge theta 1, omega 3 2 wedge theta 2 is 0. This is called symmetry equation. And the third one, Gauss's equation, d omega 1 2 is just omega 1 3 wedge omega 2 3, no, 3 2. So this is Gauss equation. Okay, and the fourth one is uh, just Kodazi equations. D omega 1 3 is omega 1 2 wedge omega 1, no, 2 3 2 3, and d 2 3 is 2 1 wedge 1 3. Kodazi equations. Okay. Well, of course, these are just consequences of the theorem we proved in the previous section. So all these formulas follows from uh, Cartan's structural equations of section 2.8. What were they? Remember, we had d theta I, omega ij, theta j, and the second was one was omega ij is summation over k, here summation over j, omega ik wedge omega kj. So for example, hence for example d theta 1. So d theta 1, the first one. How would you get this? This is just uh, theta 1. So I is 1. So omega 1, 2, theta 2. And then omega 1, 3, theta 3. Uh, yes, but omega okay. Theta 3 is just 0. So we have 1, 3, theta 3, uh, theta 3. But this is 0. Therefore, we get 1, 2 wedge theta 2. Similarly, uh, the omega 1, 3, this is just okay. 1. So I is 1 and j is 3. So the only non-zero term comes from k equals 2. So this is 1, 2 wedge 2, 3. Okay. And the other ones are similar. Okay, so I will not do them. They just follow from Cartan's formulas. So the rest is exercise left as an exercise. Okay. Now let's skip to the next section, which is called form computations. Okay. Okay. Yeah. All right. Okay. We assume the above setup again. We start with the lemma. This is called the basis formulas. If phi is a one form on M and nu is a two form on M, then we have this. Every one form is written in this form, in this form, and every two form can be written like this. Why is that? Because theta 1 and theta 3 form a basis for the dual of the tangent space, right? E3 is the normal vector, therefore the dual vector E3 is 0 on the tangent space of the manifold of the surface. Therefore, every form is written in terms of theta 1 and theta 2. But for uh, a proof, we can write down the following. Since E1, E2 form a basis for TPM at any point P of M, it is enough to check these on these vectors. So, for example, for the first one, so I'll just compute. This is a one form, this is another one form. These are just coefficient functions. I will just show that these two forms agree on the basis vectors E1 and E2. So let's take this second form, this so coefficient function, and then another coefficient function times theta 2 on the vector E1. So what is this? This is phi of E1 theta of E1 plus phi of E1 theta E2. Sorry, theta 2 E2. And this is theta 1 E1. This is E1. Sorry. But I know that these are dual vectors, right? So uh, this is 1 and this is just 0. Therefore, the result is just uh, phi of E1. Similarly, the same holds. So this gadget, I should have here, I guess 2. Sorry, 2. This is 2. Yes, 2 theta 2 on E2. So theta 1 E2 is 0, theta 2 E2 is 1, therefore this is just phi of E2. So what we see, these two forms, this form and phi, agree on both basis vectors. Therefore, phi is equal to phi of E1 theta 1 plus phi of E2 theta 2. For this second statement, nu of E1 E2 theta 1 wedge theta 2 on these two vectors. What is this? This is the coefficient function, so I just keep it outside, and then I compute this two form on these two vectors. How do we compute this? Well, this is just the determinant of what? I take the first form, compute on the vectors, and then take the second form, compute on the vectors, and form this matrix. Well, what is this matrix? This is just the identity matrix, because this is 1, this is 0, this is 0, and this is 1. Therefore, the result is just mu of E1, E2. So the result follows. this form and this form agree on this basis, hence mu is just mu e1 e2 times the two form theta 1 wedge theta 2. Okay, we have another lemma. Okay, uh, lemma. It has two parts. Uh, omega 1 3 which omega 2 3 is just Gaussian curvature as a function times the two form theta 1 wedge theta 2, and the second part of the lemma omega 1 3 wedge theta 1 plus theta 1 wedge omega 2 3 sorry is 2 times h times theta 1 wedge theta 2. Let me see. Okay. Let's see. Proof. Well, by definition of the shape operator, E of E1, S of E1 is just minus the covariant derivative of E3 along E1. This is the E3, remember, is the vector U, the normal unit normal vector. Therefore, S of E1 is just what? This is minus omega 3 1 E1 E1 minus omega 3 2 E1 E2. And similarly, S of E2 is just minus the covariant derivative along E2 of E3, and this is just minus omega 3 2 sorry 3 1 E1, no, not E1, E2 E1 minus omega 3 2 E2 E2. Uh, therefore, therefore, the matrix representation of the operator S in the basis E1, E2 of the tangent space is just what? How would you compute the matrix representation? You compute the operator on matrices, look at the coefficients, and then write these coefficients as your columns. So this matrix representation is this. So the operator S in the basis E1, E2 is this 2 by 2 matrix. I take the first coefficients and write them as the first column. This is minus omega 3 1. So if I interchange the indices, this becomes 1 3 E1 And then similarly, this becomes the second 2, 3, E1. And then here omega 1, 3, E2 and omega 2, 3, E1. Yes. All right. So this is a matrix representation of the operator S. What is the determinant of this? Well, uh, determinant is just the Gaussian curvature. So we have, and by the lemma, previous lemma, two forms are equal to each other if they agree on a set of basis elements. So now by the previous lemma, k of theta 1, so Gaussian curvature of theta 1, theta 2, and then E1, E2 is what? This is just k times, uh, well, uh, we know that this is just 1, so this is k, but this is equal to determinant of S. We know that Gaussian curvature is this. This is just simple computation, right? This is determinant theta 1 E1, which is 1, theta 1 E2, which is 0, and then theta 2 E1, which is 0, and then theta 2 E2, which is 1. So I get identity matrix here. Its determinant is just 1. So I have here k, and it's equal to this one. And what is this determinant? Well, this is just omega 1, 3 E1, omega 2, 3 E1, minus omega 1, 3 E2, omega 2, 3 E1. I guess I made a mistake here. Yeah, these are both E2, right? So this should be E2. Okay, so E1 and then E2. Yes. 1, 3, E1, 2, 3, 1, 3, E2, and then E1. Okay, so what is this? Well, this is just omega 1, 3, wedge omega 2, 3, E1, E2, right? So I have this form. This is a two form computed on these vectors is equal to this form computed this on these two vectors, which form a basis for the tangent space. Therefore, these two forms must agree. Therefore, k times theta 1, theta 2 is just omega 1, 3, and then omega 2, 3. Okay, the second statement is similar. I am not sure about this theta. Let me check. Okay. Uh, yeah, this should be 2. Sorry. Okay. Yeah. I won't prove the second statement. It is just done in a similar fashion. Okay. So the second uh, equality identity uh, is left as an exercise. Okay. Well, by the second uh, structural equation, which is called Gauss equation, we have what? We have d omega 1 2 is minus 1 3, sorry, wedge 2 3, right? We had, where was it? Yes, Gauss equation, which was this. Okay. Uh, Hence we get, and thus if we combine this with the above theorem, we have corollary d omega 1 2, which is equal to this gadget, but this is equal to what? This is just 1 2, and then 2 3 is just k times theta 1 theta 2, so this is minus theta 1 theta 2. Okay. Let me finish this uh, hour by the following remark. In the previous section, I mean section 6.1, we had computed uh, theta I and omega ij for the spherical coordinates on a sphere of radius r. Hence, from that computation, we had this. We had uh, theta 1 wedge theta 2 r squared cosine phi d nu d phi, and this is just of course minus r times cosine phi d phi d nu, and we know that d omega 1 2 is just also was this, which is just cosine phi d phi d nu. So if you compare, this result with this corollary, so by the corollary, uh, Gaussian curvature is just 1 over r squared, which is the result we expect, right? As expected. Okay. All right. Yeah, let me stop here for today. I'll see you next time. Bye.